Hello everyone, this video is about inference for the comparison of more than two population means. So today we'll see a hypothesis testing technique that is used for the comparison of more than two population means, which is called analysis of variance or ANOVA. In the comparison of more than two population means, there is one quantity variable of interest measured from G different groups or populations. So the quantity variable represents our outcome of interest or dependent variable, and the G different groups or populations represent the factor variable with G different categories. So we have two variables. One is the quantity variable, which is actually our outcome variable of interest, and the other is a qualitative variable with G different categories. So the categories of the qualitative variable represents the different populations or the different groups. So the interest here is to test whether the G population means of the response variable of interest are equal or not. And the null and the alternative hypothesis can be written as mu1 equals mu2 equals mu G, and for that of the alternative hypothesis, we may say not H0. So here, mu1 is the population mean of group 1, mu2 is the population mean of group 2, and mu G is the population mean of group G. So here, H0 represents that all the G group means are not significantly different. And not H0 represents that at least one of the G different means is significantly different from the others. So in the null hypothesis, we write all the means using this equal sign, but in the alternative, we couldn't write the means with a different from type in all of the cases. Rather, we have to say not H0. This means at least one of the G different means are significantly different from the other. Perhaps all of the G group means may be different, but the alternative actually represents that at least one of the G different means may be significantly different from the others. So the hypothesis testing procedure that is used for testing this hypothesis is called analysis of variance or ANOVA. So for conducting this ANOVA test, random samples are going to be selected from each of the G different groups under the assumption of normal distribution. Besides the normal distribution assumption of each group, we also assume that the variability of the response variable of interest is homogeneous across the G different groups. So in group 1, the distribution is assumed to be normal, in group 2, normal, in group G, normal. In addition to this normality assumption, we also assume that the variability or the variance of the response variable is homogeneous across the G different groups. So for group 1, the distribution is normal with mean mu1 and the variance sigma square. Now sigma square is the variance of group 1. And for group 2, again the distribution is normal with mean mu2 and variance sigma square. Sigma square is the variance of group 2. So group 1 and group 2 have the same variance. Similarly, for group G, the distribution is normal with mean mu G and variance sigma square. Again, sigma square is the variance of group G. Therefore, here the variances across the G different groups are the same, or they are homogeneous. So we have these two main assumptions in taking random samples from each of the G different groups. One, the response of interest is normally distributed, and the other, the variability of the response of interest is homogeneous across the G different groups. So from each of these distributions, we need to take certain random samples of group 1, random sample of group 2, random sample of group G. Then once we obtain certain random sample observations, we can determine some of the summary statistics like the sample mean of each group and the sample variance of each group. So the sample mean of group 1 is nothing but the sum of these values divided by n1. The sample mean of the second group is the sum of these values divided by n2. And the sample mean of group G is the sum of these values divided by Nj. So in general, mean of the J's group can be obtained as 1 over number of observations of that group times the sum of all the observations belonging to that group. Similarly, we can determine the sample variance of each group. Sample variance of the J's group is 1 over number of observations in that group minus 1 times the sum of the square of the deviation of each value taken from their corresponding mean. So these are the summary statistics representing each group. We can also determine the overall mean and overall variance. So overall mean is nothing but the sum of all these observations of all the G groups divided by the total number of observations. In group 1, there could be n1 observations. In group 2, there could be n2 observations. In group G, there could be ng observations. Then the total number of observations in all the groups is n1 plus n2 plus ng. So the grand mean or overall mean of all the groups is nothing but sum of all these values divided by the total number of observations, where the total number of observations is actually the sum of the number of observations of each group. Similarly, we can also determine the overall variance across the G different groups as sample variance of all the groups S square equals 1 over the total number of observations minus 1 times the sum of the deviation of each value taken from the overall mean. This overall mean is nothing but the sum of all the values divided by the total number of observations. So here these double summations are nothing but the inner summation represents the groups, the outer summation represents as of the observations belonging to each group. So the overall variance could be calculated in this form. Now the principle in ANOVA is to decompose the total variability of the data into two main components. Decomposing the total variability into two main components. Here the overall variance is S square, which is 1 over n minus 1 times the double summation of xij minus x bar the whole square. J runs from 1 up to g and I runs from 1 up to ng. So the idea is to decompose this variance into two main components. One, the variability due to the difference between the groups, and the other, the variability due to the difference within the groups. So here the between variation is usually called treatment variation. This represents the variation due to the difference between the groups. This difference between the groups measures how much the group means differ from the overall mean or grand mean. So the between variation is nothing but here x bar j represents sample mean of the J's group. So the difference of x bar j from the overall mean represents the between variation. X bar j mean of the J's group and x bar will not be equal. So there is some sort of difference. That difference is said to be between variation. So the between or treatment variation is the variation due to the differences between the groups, which represents how much the group means differ from the overall grand mean. And the Wisdom variation is usually called an error variation. This variation represents the variation in each group that could result from certain uncontrolled biological variation, technical and measurement errors, or other types of sources. So this Wisdom or error variation is unavoidable, but we need to minimize as much as possible. So here, for example, in the G different groups, we could have these observations. The observations in the first group, observations in the second group, observations in the G group. Now here, we can obtain the sample mean of the first group as sum of these values divided by n1, which is x bar 1. The sample mean of the second group, sum of these values divided by n2, which is x bar 2. Similarly, the sample mean of the G group, which is the sum of these values divided by ng. Let's say x bar g. So here we have g different sample means that corresponds to each of the different groups or populations. So the variation of x bar 1 from x bar, that means the sample mean of the first group from the overall mean, represents the between variation. Similarly, the difference x bar 2 minus x bar represents the between variation of the second group. Similarly, the difference x bar g minus x bar represents the between variation of the G group. So between variation is nothing but simply a variation between the sample mean of each group and the overall or grand mean. So these values represent between variations. And coming to that of the Wisdom variation, we need to consider that of variance. The variance of the first group is S1 square. This represents the Wisdom variation of group 1. The variance of the second group is S2 square. This represents the Wisdom variation of the second group. And the variance of the G group is SG square, which represents the Wisdom variation of the G group. So these are between variations, these are Wisdom variances. Let me go back once. Here, for example, variance of the G group is nothing but 1 over number of observations of that group minus 1 times the sum of the square of the deviation of each observation in that group minus that of the mean of that group. So this is variance by definition. The component, the sum of the square of the deviation of xij from xj represents variation. This component alone represents variation. Totally, this is a variance, but when we say variation, we are considering only this part without dividing by nj minus 1. So S1 square is the variance of the first group. The variation is nothing but n1 minus 1 times S1 square, because here this is the variance, this part is the variation, so this variation is nothing but Sj square times nj minus 1. Similarly, the variation of the second group is nothing but n2 minus 1 S2 square, and the variation of the G group is nothing but Ng minus 1 times Sg square. In general, you can consider the difference of each group mean from the overall mean represents between variation. The variance of each group represents that of within variation. So the total variation is considered in terms of what we call total sum squares, is the sum of the between group variation, which is called between sum squares, and the within group variation, which is called within sum squares. So the total variation is nothing but this, the double summation of xij minus x bar the whole square. This is the overall variance or the grand variance of all the observations in all the groups. So this is the variance. The variation is nothing but this component alone, which is s squared times n minus 1. This component alone. So this component, this total variation, is going to be decomposed into two components. This is the variation, the total variation, which is the sum of the between sum squares and that's of the within sum squares. X bar j minus x bar represents that of the between variation. Xij minus x bar j, this represents that of the within variation. That means the error is nothing but the deviation of each observation from their corresponding group mean. The between variation is nothing but the difference between the group mean and the overall mean. So here the null hypothesis is going to be rejected if this between sum square is larger than that of this within sum square. Or in other words, if these between variations are larger than that of this within variations, in that case H naught, which states that all the G group means are equal, should be rejected. If these between variations are much larger than the within variations, the null hypothesis that states that all the G group means are equal should be rejected. On the other hand, if the between variations and the within variations are approximately equal, in that case, the null hypothesis that states all the G group means are not significantly different from cannot be rejected. So if this between variation is significantly larger than the within variation, this H naught that states all the G group means are not significantly different should be rejected. Otherwise, if they are approximately equal, we do not reject this null hypothesis and we can conclude that all the G group means are not significantly different. So this formula, which decomposes the total sum square into between sum square and within sum square, can also be written as in this form. For example, here we have x bar j, x bar. Now this is independent of I. Here we have sum of I running from 1 up to ng. So this is independent of I. So instead of this sum, we can simply write ng. Similarly, this is the between variation of the j's group, sum of xij minus x bar j square. I runs from 1 up to ng. So this can be written as nj minus 1 times variance of the j's group. So in other words, the between sum squares is nothing but n1 times x bar 1 minus x bar square plus n2 times x bar 2 minus x bar square plus ng times x bar g minus x bar square. Then here we have what we call degrees of freedom, or the number of independent observations that are free to vary. So regarding the total sum squares, there will be n minus 1 observations that are free to vary. So the degrees of freedom for the total sum square is n minus 1. And the degrees of freedom for the between sum squares is g minus 1, or number of groups minus 1. And the number of independent observations that are free to vary, or the degrees of freedom for the within sum squares is n minus g, total number of observations minus number of groups. So this is the total sum square. This one is the between sum square. This one the within sum square. The ratio of the between sum square with its degrees of freedom is called between mean square. So here we have this between mean square. The degrees of freedom is g minus 1. Therefore, this value divided by g minus 1 represents the between mean square. Similarly, the ratio of the within sum square to its degrees of freedom is called within mean square. So this within sum square divided by the degrees of freedom n minus g is said to be that of within mean square. So the ratio of the between sum square to its degrees of freedom is called between mean squares, and the ratio of the within sum squares to its degrees of freedom is called the within mean squares. So the test statistic uses what we call variance ratio test. And this variance ratio test is nothing but the ratio of the between mean square to the within mean square. And this actually follows an F distribution. So like that of the standard normal distribution, Z distribution, and that's of T distribution, we have also what we call F distribution. So the test statistic based on this variance ratio test is nothing but between mean square, that is between sum square, over the degrees of freedom, that is g minus 1, over within mean square, that is the within sum square, divided by the degrees of freedom for the within sum square, that is n minus g. So this is nothing but between mean square over within mean square. So this will have an F distribution with g minus 1 and n minus g degrees of freedom. G minus 1 is the degrees of freedom for the numerator part, and n minus g is the degrees of freedom for the denominator part. So this is the test statistic that is used for analysis of variance test. So this distribution is F distribution. So this is the calculated value. The critical value or tabulated value is also determined using that of F distribution. So the tabulated value based on the F distribution is nothing but F at alpha degrees of freedom with g minus 1 and n minus g degrees of freedom. So if this calculated value is greater than that of this tabulated value, then in that case H naught can be rejected. That means the null hypothesis of no significant difference in all the G population means can be rejected. So if the null hypothesis is rejected, that means at least one of the G group means will be different from the others. At least one will be different. Perhaps all the G group means could be different, but minimum at least one of the G group means will be different from the others. And the other thing, in the case of inference for single population, paired samples, and in the case of the comparison of two population means, we have one-sided and two-sided tests. But in this case, here it is based on the ratio of that of variance ratio test, which is the ratio of the between mean square to the within mean square, which follows an F distribution. So in this case, we do not have one-sided test, or we do not call the test as two-sided or one-sided in general. So every time the tabulated value based on this F distribution is obtained as F of alpha. So there is no need of dividing it by 2. Just F alpha with G minus 1 and N minus G degrees of freedom. So we do not classify here the test as one-sided or that of two-sided tests. So the results of the analysis of variance are presented in a table form in this form. Source of variation, the variation due to the groups, and the variation within the groups. So the sum squares, here you will have between sum squares, and here you have within sum squares. And here for the degrees of freedom for the between sum squares is g minus 1, and the within sum squares, the degrees of freedom is n minus g. And regarding the mean squares, between sum squares divided by g minus 1 represents between mean square, and within sum square divided by n minus g represents the within mean squares. And finally, the ratio of the between mean square to the within mean square represents the F-test statistic. And regarding the total, here we will have the total sum squares, which is the sum of between sum square and within sum square. Then the degrees of freedom for the total is nothing but n minus 1. This is nothing but the degrees of freedom for the between sum square, g minus 1, plus the degrees of freedom for the within sum square, that is n minus g. So this sum is n minus 1. So now let's consider a simple example to illustrate how to perform hypothesis testing for the comparison of 3 or more population means, or let's see that's of the analysis of variance test. Suppose a university wishes to compare the effectiveness of 4 teaching methods: online learning, self-study, lecture, discussion for a particular course. 24 students are randomly assigned to the teaching methods with 5, 6, 6, and 7 respectively. At the end of teaching the students with their assigned method, a test, for simplicity, let's say out of 20, was given, and the performance of the students were recorded as follows. These are the records of the students who are assigned to the different teaching methods. So it says test the hypothesis that there is no significant difference among the 4 teaching methods, and also construct the ANOVA table. So here we have 4 teaching methods: online, self-study, lecture, discussion. So we are interested in comparing whether the mean score of these teaching methods are the same or not. So the hypothesis to be tested is mu1 equals mu2 equals mu3 equals mu4. That means the teaching methods are not significantly different, or the teaching methods have not significantly different effectiveness. And the alternative is H1, which is not H0. That means at least one of the teaching methods significantly differs from the others. So here when we say at least one of the teaching methods is significantly different from the others, so that teaching method may be best, or that teaching method may be or the worst one. So whatever it is, in general, at least one teaching method could be different from the others. It could have a better performance or better effectiveness, or it could have the worst performance or worst effectiveness. So let me go back to here. Here, for example, there are 5 students who are assigned to the online learning method. These 5 students have no the same score. So these differences are called within variations. Similarly, there are 6 students who are assigned to the self-study group. Even if they belong to the same teaching method, their scores are different. So this difference represents the within variation. Similarly, in the lecture, the same. We have a within variation, and here we have a within variation. So the variation within each group is said to be within variation. And coming to the between variation, here we need to obtain the average score. Here we need to obtain again the average score. Here again another average score, and here again another average score. All these averages will not be the same. So the difference among, let's say, this group means represents that of the between variation, or the variation due to the difference across the teaching methods. So the summary statistics for these four teaching methods is number of observations in the online method. We have 5, in the self-study 6, in the lecture 6, and the discussion 7. We can also calculate that of the sample mean of each group. So here the sample mean performance in the online group is 11.8, and the mean performance of the self-studies 7.667, and the mean performance in the lecture method is 12.833, and that of discussion is 8. So here these sample means are different. So this represents something like the between variation, or the variation due to the difference across the teaching methods. And let's see the sample variance of each group. Sample variance of the first group is 3.7. So that means the observations are not all the same. So this represents the Wisen variation. In the self-study, the variance is 5.067. In the lecture method, it is 3.767. In the discussion, it is 2.667. So these variations represent Wisen variations, and the difference across these means represents something like the between variations. And the total number of observations is nothing but n1 plus n2 plus n3 plus n4. That is, totally we have 24 observations. And the overall mean is nothing but 1 over n, that's 24, times the sum of all the values. So the overall mean will be 9.625. This is the overall mean. So the between variation of the first group is nothing but 11.8 minus 9.625. So the difference between this value and this value represents the between variation of the first group, or the online learning. And the between variation of the self-study is here x bar 2, which is 7.667, minus this overall mean x bar 9.625. So the difference between this value and this value represents the between variation of the second group. And the same is true that of the between variation of the third group, which is the difference between 12.833 and 9.625. And that's of the discussion group, which is the difference between 8 and 9.625. So once we have these values, we can determine the between sum square as the sum of nj times the square of the deviation of mean of the just group minus the overall mean. This becomes 126.89. Since we have here 4 different groups, 1, 2, 3, 4, the degrees of freedom for the between sum square is 3. Similarly, for the within sum square, since we have these variances, that is nothing but the within sum square is the sum of nj minus 1 times variance of the just group. So the value becomes 74.97, and here the degrees of freedom is n minus g. N minus g. So n here is 24, g is 3, 24, g is 3, so this 24 minus 3, this should be 21. It's not 20, it should be 21. Sorry, here the number of groups is 4. 1, 2, 3, 4. So n minus g is nothing but n 24 minus 4, 20. Therefore, this should be 20. It's correct. We need to consider as it is, just n minus g. So the ANOVA table can be presented in this form. Source of variation between groups, within groups, total. The sum of the squares for the between groups, it is 126.89, and the sum of the squares for the within groups, it is 74.97. The sum of the two provides the total variability for the total variation, 201.85. The degrees of freedom for the between groups, number of groups minus 1, that is 3. We have 4 groups, minus 1, 3. For the within groups, n minus g, n is 24, total number of observations in all the 4 teaching methods, minus number of groups, we have 4, then the degrees of freedom for the within groups is 20. The sum of the two provides the degrees of freedom for the total, that is n minus 1, which is 23. Now the mean square is nothing but the sum of the square divided by their corresponding degrees of freedom. So 126.89 divided by 3 represents the between mean square, 42.2967. And the sum square of the within variability, that is 74.97 divided by 20, it is 3.7485. So once we obtain this between mean square and within mean square, we can easily obtain that of the calculated value of the test statistic, which is actually the between mean square 42.2967 divided by within mean square, that is 3.7485. So it becomes 11.28. So this is the analysis of variance table or the ANOVA table. So here, since the calculated value of the test statistic, which is 11.28, is greater than that of the tabulated value f at alpha, which equals 5% or 0.05, with n minus g minus 1 degrees of freedom 3 and n minus g degrees of freedom 20. You can easily obtain this value from an F distribution. F at alpha equals 0.05 and 3 and 20 degrees of freedom. So the calculated value is greater than the tabulated value. Or you can obtain the p-value using statistical software as 0.001. So using either of the two cases, we can decide that H0 can be rejected. That means the null hypothesis, which states that the teaching methods have not significantly different effectiveness, should be rejected. If this is rejected, that means we are in favor of the alternative hypothesis, which means at least one of the teaching methods is significantly different from the others. So at least one of the teaching methods is significantly different from the others at 5% level of significance. So if at least one of the teaching methods is significantly different from the others, so the next question is which teaching method is better or which teaching method is bad. So from the analysis of variance, we only determine whether all the G group means are not significantly different or not. But which teaching method is better or which teaching method is bad, cannot be determined from the analysis of variance. So the only conclusion that we have here is at least one of the teaching methods is significantly different from the others. But which one is best or which one is bad, we don't know. So once the null hypothesis H0 is rejected in analysis of variance, next we need to identify which pair of group means are significant and which are not. Because there could be at least one teaching method better, there could be two better, three better, or even all the four may be different. Or there could be one bad, two teaching methods which are bad, three bad, all in general, all the teaching methods may have different effectiveness. So for this purpose, we need to consider what we call multiple comparison or mean separation methods. There are different mean separation methods, but the one that we are going to look at here is that of the Fisher's least significant difference method, or which is in short called LSD method. This LSD method or least significant difference method compares two means at a time. So for example, to compare the J's and the K's group means, the LSD test statistic is T alpha over 2 with n minus g degrees of freedom. T is the statistical T distribution. Alpha is the level of significance. So T alpha over 2 with n minus g degrees of freedom. N is the total number of observations in all the groups, minus g is the number of groups, times root of the Wheezen mean square. The Wheezen mean square is this one, 3.7485 for our particular example, times 1 over nj, number of observations belonging to the J's group, plus 1 over nk, number of observations belonging to the K's group. So here we pick only two group means at a time and use this test statistic to determine whether these two group means are significantly different or not. So if the sample mean of the difference between the two groups is greater than this value, we can say that there is a significant difference between the population mean of the J's group and the K's group at that specific level of significance. Otherwise, if the difference of the sample means is not greater than that of this least significant difference statistic, we can conclude that there is no significant difference between the two group means. So let's consider again this previous example on the teaching methods. Since we reject the null hypothesis here and conclude that at least one teaching method is significantly different from the other, then we have to conduct a post hoc analysis, or what we call mean separation method, next to that of rejecting the null hypothesis. So first we need to sort the teaching methods based on the sample means. So lecture has the largest sample mean, 12. Next the online learning, which is 11. Next discussion, and lastly self-study. So here we could make three pairs of comparison: lecture with online, online with discussion, discussion with self-study, because here we sorted based on the sample means as lecture, online, discussion, self-study. So we could make three pairs of comparisons. So for the comparison of lecture and online, the sample mean of lecture is 12.833 minus the sample mean of online is 11.8. So the difference is 1.033. The LSD test statistic is T alpha over 2 with n minus g degrees of freedom, root of the Wheezen mean square, times 1 over number of observations of the first group and plus 1 over number of observation of the second group. So the Wisdom mean square is here, we have already obtained 3.7485. So the value t, you can easily obtain t alpha over 2, t 0.05 over 2, that is t 0.025 with n minus g degrees of freedom. That is n is 24, g is 4, 20. Therefore, t 0.025 with 20 degrees of freedom, the value becomes 3.153 times root of the Wisdom mean square is 3.7485 times 1 over number of observations of lecture, we have 6 plus 1 over number of observation of online, 5. Then it becomes 3.696. Now 1.033 is less than 3.696. So that means there is no significant difference between lecture and online. No significant difference. Going to that of online and discussion. The mean of the online group is 11.8. For discussion it is 8. So the difference is 3.800. We can also calculate here the LSD value. The only difference is going to be here on the number of observations, 1 over 5 number of observations of the online group plus 1 over 7. 7 is the number of observations of the discussion group. So it becomes 3.574. Now 3.8 is greater than 3.574. So we can say that there is a significant difference between the online and discussion teaching methods. So for the third, here we have discussion and self-study. We have the mean of discussion 8 and the self-study 7.67 and the difference is 0.33. And here the LSD value becomes 3.396. So is the difference 0.333 is less than this value 0.333 is less than 3.396. So there is no significant difference between the discussion and self-study teaching methods. So the only difference that we observe is online and discussion. So here lecture is better than online based on the sample, means online better than discussion based on the sample, means discussion better than self-study. But the one that are statistically significant is online and discussion. And we know that here lecture and online are not significantly different. So since here online is different from discussion and here lecture and online are not significantly different, that means lecture and discussion are significantly different. So lecture and online are better than that of discussion, and here self-study is not better than that of discussion. So of these four teaching methods in general, the one having a larger, significantly larger mean is that of lecture and online, which are not significant, but these two lecture and online teaching methods are better teaching methods compared to the other two teaching methods, discussion and self-study. So lecture and online teaching methods are the better teaching methods compared to the other two teaching methods. So we can conduct mean separation methods using the least significant difference method in this way. So this is all about today's video.